Okay. So let's see this. So I don't know how much you we were interrupted, but I don't know where exactly. So maybe I go again through this. I want to prove this theorem here. Go through it. I have a Gröbner basis of the ideal I with respect to a term order of elimination type. Then I define the set GL consisting of those elements of the Gröbner basis depending on the last variables. And the claim is this GL is a Gröbner basis of the elimination ideal. Okay, so I went through the proof. GL is in IL. This is a trivial inclusion. Then, what did I do? The last thing I showed that GL is a Gröbner basis of the ideal generated by GL. And I think that's where I was interrupted. I argued that every element F of this ideal generated by GL reduces to 0 mod GL. And therefore, by our general criteria about Gröbner basis, I know this. Okay, this is a characterizing property of the Gröbner basis. Not one that is easy to test, okay, but it characterizes. Okay, and to complete the proof, okay, remains to show, okay, let's do it for the sake of clarity. The only thing that remains to show, let me put this claim, that actually the GL generates the elimination ideal. And otherwise, let's say, if I had some F in EL, which was not here in that ideal, then right. So then F would have a normal form. F had normal form different from 0 mod GL. Okay, because this is a way to test. If I have a polynomial, I want to know, is it in the ideal? I have a Gröbner basis. I just compute the normal form. It's unique, the normal form, and right. Okay, but I know from the above, F reduces to 0 mod GL. Okay, let me put here a star. Okay, and this is a contradiction to uniqueness of normal form. Contradictness, uniqueness, normal form. Modulo Gröbner basis. So I'm done. Okay. Okay, so this is a very useful theorem. So let's see how. Let's give an. Okay, I have one application. I have one example. And this example is basically taken from Cox's Lidl-Oshie, I think. But let's go through it because it involves calculation. But I think it's a very good illustration of what is going on. So I have an ideal generated by 3 polynomials, F1, F2, F3. Okay, and let me write these polynomials. Okay, F1 is, I have 3 variables, so x squared plus y plus z minus 1. F2 is x plus y squared plus z minus 1. So maybe I should write variables x, y, z. And F3 is x plus y plus z squared minus 1. So I have 3 polynomials in 3 variables. And let's think of the complex numbers as the base field. So, right, so what would you expect? So typically one would expect a finite number of solutions. Okay, and the Gröbner basis allows us to compute it. So the reduced Gröbner basis, with the help of the computer, I compute the reduced Gröbner basis, which is unique, with respect to the lexicographic ordering, x greater y greater z. Okay, And okay, I don't want to, one could, but I don't like to compute it by hand. So the computer gives me the answer. It gives 4 polynomials. And I just copy them. So G1 is x plus y plus z squared minus 1. G2, okay, what happened? Sorry, I have. Oh, yeah. Somehow I realized I started writing that at the beginning, but it doesn't matter. Okay, I need a little bit more board. Okay. Okay. Let me give more board. Okay. Okay, I continue with the G2. Y squared minus y minus z squared plus z. G3 yz plus 1/2 z to the 4 minus 1/2 z squared. I hope this is all correct. Okay, G4 is this, z to the 6 minus 4z to the 4 plus, you see the element, okay, the polynomials in the Gröbner basis are already ordered in a good way. So we see the last one, the G4, only depends on z. Okay, so we can see, maybe I can write in color, the first one depends on x, y, and z. The next two do not contain x anymore. So I can say x is eliminated. And in the last one, x and y are eliminated. Okay. So it's a concrete example. So the concrete numbers are not important. You will see the principle, general principle. So therefore, now I apply my theorem. It says the second elimination ideal is the one where the x is eliminated. Sorry, the second elimination ideal is the one where, okay, it's a bit strange. Let's write first the I1. That's more meaningful. Okay, when x is eliminated, so what remains is G2, G3, G4. Okay, and if I eliminate x and y, what remains is a single polynomial G4. Okay. So, okay, so this is useful, this information, if you want to actually compute the solution set. Okay, can use this information, okay, to compute the solutions of the system, okay, of the system F1 equals F2 equals F3 equals 0. Okay. So what we first do now, this is just general scheme. So we find, okay, we go in the reverse order. We start down here and then we go up. So I look first at G4. G4 is a polynomial only in the variable z. So I find the solution of that univariate polynomial. Okay, find solutions of G4. Okay, so I don't tell you how we find this. I mean, let's assume we have a procedure to find the solutions to polynomials in one variable. This is not a trivial task, as we know, but assume we have one. So the idea of this elimination is to reduce the solution of systems to the solution of univariate polynomials. So we assume we have a black box that does it. And in this concrete example, I can say what it is. Okay, miraculously or by choice, by choice of the polynomial these factors in a nice way, and this is just a nice made up example. Okay, so it factors. So this degree 6 polynomial factors this way, and we have the 0 set. Okay, I don't care about multiplicity. I just write 0. It has multiplicity 2, but I don't care. I have 1, also multiplicity 2. And then these two things coming from the quadratic factor. So this is the 0 set. Okay, you see, I have 4 solutions here, but there is multiplicity, which I don't haven't written. Now 2. Now we just plug in these solutions in the remaining equations. So plug in 0. I call it zeta. Okay, zeta will be here in G2 and G3. Okay, the G2 and G3, okay, are those. Okay, there is no X. So I will find equations for Y. So I get 2 equations in the variable Y. Okay, solve. So let me write this. So I have this Y. Yes. So these are 2 polynomials in the variable Y. So typically there will be no solution. Okay, if this would be a generic example, there would be no solution. But in this example, it turns out there is one. Okay, so the resultant of these polynomials actually vanishes. So one solves, computes. Okay, so for Y, when I say solve, I again would apply to my black box in a way. Then I have it. And then in the third step, okay, I plug in the eta. Okay, the eta. Okay, now here, the z, I plug in the zeta, and here I plug in the eta, and then I solve for x. Of course, this will be very simple. It's just a linear equation. Okay, find 0 psi of the first one. The variables here x. Okay, so maybe I should have write a small x. Okay, so obtain. Now, if one does this calculation, I don't want to bore you, but one gets the following: 0 set. Okay, is this 1 0 0 0 1 0 0 0 1, and then 2 more, -1 plus square root of 2. -1 plus square root of 2. Okay, same component and the same game with the minus. Okay, I could have written it in a more compact way, but it doesn't really matter. Okay. Okay. So I have 5 solutions. 5 solutions. Okay. Let's see. Interesting. Anybody of you has ever heard of Bézout's theorem? No.
Oh, I haven't, but I have heard of the BKK theorem.
Oh, that's more sophisticated. Yeah. Okay.
Yeah, which relates this the number of toric solutions with without where the coordinates are at 0 to the
right. So it expresses the number of solutions. Let's by a mixed volume, right? But okay, but the Bézout theorem is even simpler. So let's see. I have here polynomial. This is a quadratic polynomial. This is also quadratic. This is also quadratic. I have 3 quadratic polynomials. Okay. And the Bézout theorem says that if you have three quadratic polynomials in three variables, the number of solutions that you get. Typically, let's say, if you look at the solutions in projective space, you get 2 to the 3. So the product of the degrees is the number of solutions. But this is only true, okay, this is true when you count, you look at solution in projective space and you count solutions with multiplicity. Right, then it is true. Okay, so what we have here, we only get 5. Okay, 5 solutions. So I think what happened, I mean, only 5, 5 is less than 8. I think what happened is not that we missed solutions in projective space, there is a problem with the multiplicity. Okay, if you would count solutions with multiplicity, we would get 8. You can already see, okay, I didn't define rigorously what multiplicity means, but you can already see here, when you look at this, okay, there is multiplicity somehow hidden there. Okay. So this method, this was just one example, and I don't even fully explain it, but this is a method that works in principle. Yeah, method works in general in a way. In general. Okay, but there are of course many things to discuss if you really want to understand it. So this is the topic of classical elimination theory. So maybe that there is one issue that I didn't address at all, but if you look at the books by Coxley, Lochy, it is addressed. It may be that if you have this procedure, what may happen at some moment, okay, let's explain in this example. Maybe you have already found the Z here, and then you have found the Y, and then you want to find the X. And it may be that is not always extendable, okay? So there is, in this example, of course, it's not a problem because the F1, where is it? The G1 is a linear thing. So there are some additional issues related to resultant that make this theory not so trivial on a way. Also, maybe it's also interesting that this is what people did in the 19th century. They didn't have the notion of a Grabner basis, but they did it anyway. Okay. Right. But if you have a Grabner basis, you have a clear algorithmic concept that tells you how to do it in principle. Okay. Okay. So this is just the illustration. So there are, okay. So my plan is to, once we have this concept of Grabner basis, just show you all the possible applications it has. And these applications, this is really easy to describe what's going on. Okay, so but maybe, right. I want to, okay, okay. I have some remark here, which is a preparation for what is going to come. Let's say I have the following ideal. Consider this ideal. Okay, maybe I say the following. I have polynomials f1 up to fr in the variables x1 up to xn. So this is okay. Okay. And then I consider the following ideal. I, which is generated by, okay, I take additional variables y1. Also for each polynomial, I have an additional variable, and I look at this. Okay, so y1 up to yr are additional variables. Then I look at this ideal. So this is a very useful ideal. Okay. Okay. So what I claim then, there will be more reasonings in the argument, So one thing I claim is I intersected with this polynomial. I just write kx, abbreviates this, is 0. Okay, what is the reason for that? Let's say first proof. I give 2 proofs. I will explain what's going on. Which one do I first? Let's first do the algorithmic thing. So I have here a Grabner basis. So this collection of polynomials is a Grabner basis. Okay, with respect to a term order where the y's, these yj's become the leading terms. With respect to, say, lex, such that the y's are large. Okay, let's say I take this one. Okay. Okay, so then the y's are the leading terms. They are pairwise co-prime, and then we can apply this Buchberger criterion. We see it's a Grabner basis. We had it already. Okay. Good. Now, but now we can apply our theorem. Okay. Let's say I want to eliminate the variables. Eliminate. Sorry. Right. Variables. Y1 up to YR. Now I have, this is now easy because this lex term order is a elimination order. Okay. So I want to compute the elimination ideal. And how do I do that? Yeah, from this Grabner basis, I just pick those polynomials that do not depend on the y variable, but there is none, okay? Because all of them depend on some y. So now I apply the theorem. So the theorem gives me, looks a bit stupid, but the empty set is Grabner basis for the elimination ideal. Okay. But okay, the empty set generates the 0 ideal. So I conclude this. Okay. Okay, second proof. And this is tells us what's going on geometrically. Okay. Second proof. Maybe I move this down. So if you see this polynomials, you should think of the graph of a map. So I have a polynomial map. Let's call it F. It goes from K to the N to K to the R. Okay, with components F1 up to F4. So I have my polynomials, I combine them into a polynomial map. Okay. Okay, it's nice. Let's do a picture. I always like pictures. Of course, I can only do a 2-dimensional thing. Okay. So I look at the graph of this map. So the graph, I recall the definition, is the collection of these points, let's say x, f of x. Now these are small x, where x is in k to the n. So this is a subset of the product. Okay, so I'm sure you know that. This is the graph. Okay, and the image, so if I take, sorry, what happened here? How do I get it? Okay, so I take the projection now to the second component. So I project to k to the r, and then what do I get here? So anybody can tell me what will be the image of the graph under this projection? So if you want, let's say I have here x, y, and I project to y.
The image of f?
Yes, will be the image of f, correct. So this is the map x, y goes to y. Okay. Okay, good. So, right. So, okay. But you see, I, this ideal, okay, where is the ideal I? Where is it? Here, this ideal I. I mean, this is the vanishing ideal of the graph. This is the vanishing, okay. This gives me the equation describing that I have a point in the graph. So so this is the geometric meaning of this ideal I. Okay, so now we understand geometrically what it is. Okay, but now we can also apply our geometric principle that I recalled at the very beginning. Maybe I go back the very beginning of our lecture. Maybe is here. Geometric meaning of elimination ideals. Now we can apply this. Okay, yeah, I have a projection. The projection to the last of from x comma y to the y. I have, okay, my ideal, the zero set is the graph, etc., etc. So what do I get? Okay, I see that the image, okay, I can say I take the image. Actually, the Zariski closure of the image, okay, is the zero set of the elimination ideal. And the elimination ideal is just I intersected with kx. Did I say it right? Okay, this is good, but right. This is good, but I don't want to do it. Actually, I want to, this is good. Also, okay, this was the, I used this, let's call this pi 2, this projection, this was pi 2. It's easy to get confused here. Okay. But I also can use pi 1. Also consider this projection. Now I project to k to the n. This is pi 1. So x comma y is mapped to x. Okay. But now the image, what is the image? K to the n. Okay. Image. Okay. It maps, let's say pi 1. Graph of phi is all of k to the n. Okay. And I apply the general principle, the theorem. The theorem tells me that the Zariski closure of k to the n, now of course this is just k to the n, is the zero set of I intersected with this. Oh, sorry. Nobody complained, but I made a mistake here. This should be y. Sorry about that. And here I have x. Right. Okay, here there was y. I've corrected it. Now here I put x. Now you see, this is only possible if I intersected with kx equals 0. So now I have my second proof that this is true. So I think this is very useful to see how these things are connected. Okay, so we have seen like 2 applications, if you want, of our general theorem, geometric interpretation of elimination. Okay, in one application, like the result is more or less trivial, the elimination ideal is 0, and the other one, it's not so trivial. It describes me the image, or Zariski closure of the image, with the same ideal. Okay. Questions on that?
Can you maybe explain? Oh, I don't know how I should ask that, but I don't see why this Zariski closure of the image is that.
Where are you exactly? You
So
mean
the Zariski closure of the image is the vanishing ideal of exactly that because of
why? Oh, this.
not vanishing ideal. We see with zero set of yes.
This was the right. This is the theorem. I applied the theorem. The theorem that gives me the geometric interpretation of elimination ideals. I just applied the theorem. So it's not clear. I mean, I proved that and I just applied it. This is the theorem. And here I applied the theorem twice. I'm for both projections. Okay. Okay, then maybe let me go on. I mean, if you can clearly formulate your question. So that was right. Okay, actually, I want to, this will be on the exercise sheet, okay? But let me put it here because I want to refer to it. So this is an exercise that hopefully will end up on the exercise.